pleasure to have Giovanni Felder from Zurich. And we're going to talk about the master equation.
Thank you very much. Yes, so we'll talk about the classical master equation, which is maybe another name for the Maurer-Cartan equations. So I'm not sure it fits very well in this program, but there will be some things which will, some Gerstenhaber algebra, some deformation theory will appear. So, so let me try to motivate this. I will start with some kind of historical introduction. So in general, the kind of problem one is considering is this oscillating integrals, maybe f, some function times exponential of I as let me call it as 0, some function as 0, and you integrate over some space. And so the question is how this behaves asymptotically for h bar go to 0. And so what I'm talking about comes from gauge theory, where this is actually an infinite dimensional integral. But what I would like to tell you is that this story is interesting also in finite and non-trivial infinite dimensions. And so typically this kind of asymptotic behavior is computing by looking at critical points of S0. And so you pick a critical point of S0 and you expand around this critical point, and this gives you some asymptotic expansion. So this works well if the critical point is isolated. But if the critical point is non-isolated, then you have a problem, because the usual saddle point method doesn't work. The Hessian is degenerate, and you have to invert the matrix of second derivatives of S0 to write down this asymptotic expansion. So the simplest reason for such a function to have non-isolated critical points is if you have a symmetry, like you have a group, a Lie group action. So you don't have critical points, but you have critical orbits, and so you want to integrate over the orbit space. And so this is, maybe I will give this as a motivation. I will explain in this example of a group action how this story here is related to Maurer-Cartan equations or master equations and symplectic shifted -1 symplectic manifolds. So this is an old story. This is due to Fadeev Popov. Uh, 1967. So let me and I will formulate it in some kind of. So then, I think this was the first paper. Then there was Becky, Rouet, Stora, Tutin, 1970, around 74, and Jean-Zine Justin. So it's an old story. So they were considering this for gauge theory. So it's an infinite dimensional such integral over all connections on a bundle. And so I will try to explain the Fadeev-Popov formula in a kind of classical terms, without trying to avoid for the moment supermanifolds and Berezin integrations. And so the formula we'll present will use the later understanding of the Fadeev-Popov formula due to these people. And then Batarin Vilkovisky I will quote later. So let us consider a simple situation where you have some X manifold or variety, and you have a say connectedly group action. And G is a Lie algebra of G, and let's think about the nicest situation where, say, X is some principal G bundle. And suppose you have omega some volume form on the quotient space. So let's suppose it's smooth. And you have a function, so maybe two functions f and s0 invariant functions. on X, G invariant functions. And then the question, and then of course you can do this integral over the orbit space of f of I h by S0 omega. And so, Felder-Popov considered this case in the case of gauge theory. So now X is a space of all connections on space-time, on R4. Okay, so so they want to integrate over the quotient space, and express this as integral over X of something. And of course, you know, in the case of gauge theory, this is a very reasonable thing to do, because X, the space of all connections on R4, is an affine space. And the trouble with G is that the action of the group is nonlinear, but upstairs everything is nice and linear. And so that's why you want to do that. And the kind of formula they propose, which I try to explain in classical terms, will be like this. So first of all, you will not integrate over X, but you will integrate over some bigger space, like X cross. Well, so maybe, okay, there are two versions of this formula. So let's suppose, so let's consider the very simplest formula. So you have X mod G, and you have the orbits of G. And now the simplest thing you may think of doing is to choose a section, sigma, and integrate over sigma. And then, of course, you have some formula for change of variables, which will tell you how to relate a function here to an integral of this type as an integral over sigma. You will have some Jacobian of change of coordinates, and this is what they do. But let me reformulate this. First of all, if omega is, so we have omega is an invariant form, so it is on the top, is a top form on the quotient. And now this is the same as having an invariant form on X, I don't know, top G. Because how does this work? So, I mean, you have a map in this direction, so you have some top form here, so it will be given by some omega, I don't know, alpha wedge, and see some top element here will be, I don't know, A1 wedge AD in the Lie algebra. And now to these elements of the Lie algebra, there corresponds vector fields on X. So you can contract, and maybe this is a good occasion to introduce this notation. You can consider the corresponding polyvector field, which is psi of A1 wedge psi of AD. And so psi is the action of the Lie algebra, G to tangent vectors, vector fields. So you map. So this map here is given by the contraction or the interior multiplication of alpha. So if you do that, you will get a basic form on X, which is the same as a form on the quotient. And now, so the Felder-Popov formula says that this integral here is equal to integral over sigma cross 0 of f exponential of minus 1 I plus I s. So let's say that the image of omega is omega tilde here by this isomorphism. And so the formula can be written as a polyvector field. So this will be a polyvector field. We had this notion on X cross G star. So this you can also think of as a top form on X cross G star. Invariant. And so you have a polyvector field, and then by interior multiplication, this will act on omega t. So and what is this S? So S will have the following form. It will start with this invariant form S0, and then there will be S1 plus S2. So S1, right, so what is maybe I should define again T-poly. We had it in some lecture, but maybe not everybody was in that lecture. So this is Y is the sections of the exterior algebra of the tangent sheaf. And so, so what is T-poly? So in T-poly, you will have, it will be T-poly of X. Then you have functions on G star, which is a symmetric algebra on G. And then you have G star. So what is S1? So S1 is will be in a tangent vector times G star, which is here. So this is the action. It is psi. It is dual to psi. The action. And S2 will be in wedge 2 of G star times G. It is 1/2 of the bracket.
Why do you say dual to psi? It is exactly.
Yeah, I don't know. It is a dual map because psi goes from G to Tx, and I regard this as an element of this.
Okay.
It is the same, right? Or it is equal, but you have to it's actually the transpose map or something. Okay, so right. So this is the Popov formula in some kind of reinterpretation. And so now the point is that this obeys the master equation or Maurer-Cartan equation. So this is on this space here you have a commutative product of degree 0 and a bracket of degree 1. So for the moment you can think of Z mod 2, but later it will be important to have a grading, Z grading, and then you have to put this in negative degree. So this will be a non-positively graded algebra. And so the claim is that S is equal to 0, which is a classical master equation. And now what is a quantum master equation is important. So what you would like to have is that this is a closed form. And this is equivalent to divergence, more or less by definition of divergence of this polyvector field. Is equal to 0, and this is the same as of the h bar divided by I plus S plus 1/2 SS equal to 0. Okay? And this is a quantum master equation. Right. And now, so for this kind of to make sense, you want this to be 0, and you want also f, which will be invariant, will be a cocycle for the corresponding cohomology, given by div plus bracket with S. But in this case, you have a stronger equation which holds, which is that both terms are 0. So in this case, you have that div. So both hold separately. But in the kind of general theory, you want this equation, so the quantum master equation. Right. So, so this was Felder-Popov in essence. So Felder-Popov wrote a formula which is equivalent to this by writing the formula, the determinant of the change of variables. And then Becky, Ruiz, Torah, and Tutin noticed that there is a cohomology related to that, that you can construct some something which later was understood as a bracket with S, a differential, and that for this observable f, this function that you can to put there have to be, so the fact that they are invariant means that they are cocycles for this differential. And later, probably with Dean Justin, but better with Patain-Vilkovitsky, it was discovered that this is kind of the important equation. And then more examples of degenerate critical points came up in quantum field theory, and people try to generalize this story here to kind of integrating over orbit spaces, even if the orbits are not orbits of a group, but are leaves of some distributions for which S0 is invariant. So S0 is invariant on the leaves of some distribution of planes. And there are some crazy examples also where you have some degenerate critical point, and you have a distribution of vector fields which kill the action S0. And but this distribution is not integrable. It will be only integrable on the critical locus. So you have the critical locus of the function. There you have some vector fields which annihilate S0. And so on the critical locus you have a nice foliation. But outside the critical locus, this distribution is non-integrable. And people still want to make sense of integrating over the orbit space, and try to write a generalization of this formula which makes sense, which is kind of independent on choice of sections. And so the observation of Patain-Vilkovitsky was that it is too complicated to try to describe all these possible symmetries by distributions, and they developed a kind of formalism which is based on this equation, and which says that whenever you have a solution of this equation, then you can do you can integrate over a section, and it will be independent of the section. And the way this is formulated, but I will not go into this because I will be mostly concerned with the classical case, is that this integral here is actually thought of as an integral, a Berezin integral, over some supermanifold, which is a odd cotangent bundle. And this equation here will guarantee that the integral is invariant under deformations of this Lagrangian cycle on which we integrate. So this is a quantum, but today I will explain the classical equation. And in fact, the way you construct solutions of the master equations in this sense is first to start from a solution of the classical master equation, namely only this term here is equal to 0, and then perturb, because h bar is small, a formal parameter. So given a solution of the classical master equation, you try to find corrections to it, which depend on h bar, which will satisfy the quantum master equation. And for that you need there are some obstructions which are in the cohomology of the classical master equation. So the classical master equation and the cohomology of the bracket with S are the ingredients which then help you to find solutions of the quantum master equation. So today I will talk about the classical one. And so the kind of problem is so this is Batalin-Wilkowiski really. They start from S0 and they say that out of it you can construct a solution of the quantum master equation. And so for this process, Batalin-Wilkowiski gave some kind of recipe. How to, given S0, construct S. In this recipe, you have to make certain choices, and our goal was to try to understand mathematically what these choices are, what is this construction here, and prove that the S that you construct in this way is kind of uniquely determined by S0. And so in this case, you start from S0, you apply this construction, you get S, and it will be independent of the choices you made to do this construction. This is the goal. So this is work with David Kashdan. Joint work with David Kashdan. Okay. Right. So first of all, I will try to explain what this is, and for that I will need to introduce the notion of graded manifolds in the version we need for this construction. So the construction I described can be done with Z modulo 2 grading, but it's better to have a Z grading in the general case. So we need something called graded manifold. So this you can do in various contexts. So X could be an affine variety, smooth. So we'll talk mostly about this case, but it could also be a C-infinity manifold or a complex manifold. So, but it should be smooth. And so now, by definition, a graded variety we support X is a ring space V. Well, so X is, say, an affine, smooth affine variety, and OV is a ring of a sheaf of OX algebras, and locally isomorphic to the symmetric algebra of some graded vector bundle. Completed, and I will need to say something about the completion. So E is a locally free sheaf for a vector bundle, and this is over OX. A graded So E is a direct sum of EI, and each EI is a locally free sheaf. So here I is in Z, and so one has to be a little careful because we have both positive and negative degree. But we will take out the degree 0 because it will already be contained in X, in the functions on X. And here we have each of them is of finite rank, but the whole thing can be infinite dimensional. So I need to say something about the completion because it's a slightly subtle point. So in this Faddeev-Popov case, everything was kind of finite dimensional, but in general you have an infinite dimensional story, and so one has to be a little bit careful. And so what is this completion? So if you have, if you start from the symmetric algebra, completion. So then this is a graded algebra, and it has a filtration. So we have Fp is the ideal generated by sections, by elements of degree at least p. P is at least one, say, maybe 0. So you have Fp, so this is F0, and it will contain F1, F2, and so on. And so we take that filtration, but we have to take it degree by degree. So sim hat is direct sum of degree I, and this is a completion with respect to this filtration. I should be outside.
Giovanni?
Yes.
I'm not sure which degree you are talking about when you say at least degree P. Is it the...
So E is a graded vector bundle, so you have on the symmetric algebra you have a degree, sum of degrees of factors.
Then why sim of E is actually F0? Because you might have people in negative degree.
Yeah, but it is the ideal generated.
Oh, ideal generated by. Okay, thanks.
So.
Sorry, it's probably the third time I asked the same question.
Okay. Right. So this is the construct. So it's again graded, but in principle you have infinite set. So this is right. So now, so this is kind of the general story, and then so now suppose such a variety is called non-negatively graded. If the part of degree I is 0 for I smaller than 0, and in this case you can construct the cotangent bundle, the shifted cotangent bundle, which is called T star minus 1. Of V you can shift also in some other directions, but here we shift by minus 1. It will be X, the support of V, and the symmetric algebra completed of TV shifted by 1. So this will be our right. So TV are the derivations of OV, which is also graded. So these are these are shifted cotangent bundle, and so this shifted cotangent bundle, you have the structural P0 algebra, I think it's called nowadays. So it's a sheaf of right. So this thing here is a sheaf of P0 algebra. Namely, there is a product, associative commutative product, graded commutative product of degree 0, and the Poisson bracket of degree. Okay. And the Poisson bracket, the bracket is induced by the bracket of vector fields. This is of degree 1. Right, so it is a little opposite to the case that we heard of deformation quantization, deformation theory, where you, in this convention, you would have a bracket of degree -1 instead of 1. Right. So, so what is the basic example of such a thing? The very simple. And locally, everything is more or less like this. It is that you take, I don't know, OV, maybe global sections. So V is an affine space, so it is K. So maybe K is over, everything is over K of characteristic 0. Complex numbers, if you like. So you could have something like this, with the degree of xi equal to di, and it's, I don't know, equal to 0, and O t star minus 1b will look like k of x1 star, x2 star, and so on, where the degree of xi star is minus di minus 1. So this is the thing, and the bracket between such coordinates is delta ij, and it is 0 in the other cases. But here you have to complete, which means that you will have to take a formal power series, but so this will be a direct sum of graded components. In each graded components you take formal power series, all of whose monomials are of the same degree. So now here we have such a Poisson algebra, and then it makes sense to consider the solutions of the master equation. We have a bracket. So the solution of the master equation, classical master equation, is S, where S is a section of O t star minus 1 V. Maybe I should write it in this way. the global section of this of degree 0. And if you have a solution of the master equation, then you have a complex, which is called BRST, in honor of Beckir, West, Torat, Utin, which is maybe sheaf of complexes, P0 algebras, with differential bracket with S. And so one important, when you have such a situation, you have some symplectic manifold, -1 symplectic manifold with a differential. Then you will always have something like, maybe nowadays it should be called the underlying derived scheme. So it is something which is concentrated in negative. In non-positive degree. Namely, you have this ideal. So maybe I will first write it, O T star minus 1B divided by I. Where this I is another name for F1, the idea generated by elements of positive degree. So for degree reasons, this idea is preserved by the differential, so it makes sense to take the quotient. And this is something which is concentrated in non-positive degree. Right. Okay, so the next thing I want to say is the definition of a BV variety, Bataille-Vilkovitsky variety, which is a kind of an axiomatic definition which encodes what Bataille and Vilkovitsky constructed. And then I will say that something which obeys those axioms is uniquely determined by S0. Okay, so again, suppose that S0 is a function on an affine variety. And singular. So now definition, a BV variety, Bataille-Vilkovitsky variety, we support X as 0. So it's a pair VS, where V is a graded variety, a positively graded, not negatively graded graded variety. We support X. And S is a function on the cotangent bundle of V of degree 0. Such that three conditions. First, that S is the same as S0 modulo this idea generated by positive degree, modulo I. Okay, modulo terms which contains elements of positive degree, it is S0. Second, of course, is a master equation. And third is a condition which will make it unique up to suitable equivalence. That underlying scheme is acyclic, namely the cohomology sheaf of O T star minus 1V by this ideal is cohomology sheaf is equal to 0 for all I different from 0, or smaller than 0, because anyway it is concentrated in negative degree. Okay, so these are the axioms. So this is kind of, we try to encode what people constructed. So you look at an S, which is a solution of the master equation, which starts with a 0 in some sense, and you add terms to a 0, as we did in the case of Popov. And the additional condition is that this underlying scheme has no cohomology in negative degree. Right. So this last condition is a little mysterious, if you like, but it is what you need to get this unique solution. And then, so now before I explain, I say something about existence and uniqueness of such solutions, let me write some consequences. Suppose you have such a BV variety, then you have a complex, and then you can say something about the cohomology. So if you remember the motivation, this cohomology should have something to do with the critical locus, right? But this is not in the axioms, but it is a consequence that this cohomology will know something about the critical locus. So let me explain the relation to the critical locus. So, right, so out of S0, so you can construct the following map. If you like, the beginning of the Koszul resolution. So you have the map from tangent sheaf, so you have here a vector field, and you map it to a function just by sending a vector field to its action on the function S0. Okay? And so the kernel of this map is a sheaf of Lie algebra, it's called L. These are all the vector fields which annihilate S0. So this is a Lie algebra, it's a sheaf of Lie algebra of infinitesimal symmetry. And the co-kernel is of course OX modulo image of DS0. Is a ring, is a Jacobian ring, maybe I call it J of S0, Jacobian ring. The functions on the critical set, if you like. It is the quotient by the ideal generated by partial derivatives of S0. And L acts on the Jacobian ring. And so it's an algebra, and you have a Lie algebra acting on it. And now the claim is that simple consequence of the axioms. So suppose ds is a BV variety with this support. Then first of all, the cohomology sheaf BRST cohomology sheaf has support on the critical locus of S0. So outside it is 0. And the second is that HI is equal to 0 for I negative. This is actually a consequence of the axioms, is easy. And H0 are the invariants in the Jacobian ring. So the functions are annihilated by the vector fields in L. Okay, so you can think of them as the invariant functions on the critical locus. So we'll say something later about H1, but this is kind of the first remark, that this axiomatics knows about the critical set. Cohomology will have support on the critical locus, and the cohomology in degree 0 are the invariant functions of the critical locus. So, one example of this story is a Fadeev-Popov. Another example, which is a trivial example, but it's actually important to keep track of it. So the trivial example is you take the support to be a point, and the functions on V are, so V is an affine space but graded. So you have a variable x and a variable y of degree d, some positive number, say, degree y equal to d plus 1, and then O functions on t star minus 1 v k of x, x star, y, y star. Degree of x star is minus d minus 1. Degree of y star is minus d minus 2. And then you can construct S by saying x star y. X star y has degree 0. Okay, so this is and you can easily check that this satisfies the classical master equation. And
Could you start from an S0 and show us what S1 and S2 are? Or you don't have an S0?
so S0 is 0 if you
because
like.
here you have S0 and
Right.
we lost track of S1 and S2 completely.
Okay, so here this is very trivial. Even
So this is S1 or S2?
so this is S.
No, I understand it's S, but if you start from S0, you wrote something for S1 and S2, starting from S0.
Right, but what you have in general is S. You don't have S1 and S0. So S1 and S0 were just there to write it.
But yeah, that was my question. In the theorem, you have S0.
Yeah, you start with S0 and you construct S. There is no S1 and S2. You can think of S0 to be S to be S0 plus S1 plus S2 plus S3 and so on, according to the filtration. But
So you don't take S1 and S2 as in the formula which you showed us.
Right.
In this.
No. So that is a special case where you have. So that is a special situation, right? Where you have when these vector fields come from the algebra action. But in general, you will have S. So this is an example, and it's a trivial example. It has zero cohomology, so it's a cyclic. So the BRST cohomology. is just concentrated in degree 0 by constant sheaf. So why is that? Because if you take S of x, this will be y, maybe up to signs. S of y star is equal to x. So and S of the rest is 0. So the cohomology is completely trivial in this case. So this is a trivial example, and using this trivial example, you can construct many solutions of this. So suppose you have a BV variety, then you can multiply by the trivial example. So if Vs is a BV variety, then also V times some affine space, maybe T like trivial, so you can add some stupid factor T. T is an affine space, spec of this. And so then also with the same support and with quasi-isomorphic. BRST complex. So there is a stupid way to construct new solution out of old, which is just taking the product with a trivial solution. And it will be very strongly quasi-isomorphic, namely you will have quasi-isomorphic as a sheaf of P0, differential P0 algebras. Right. So the claim is that given S0, there is a unique PV variety up to this trivial stuff. So let me formulate it a little bit more precisely. Let's just continue here. Called stable equivalence. So suppose Vs and V prime S prime are BV varieties with the same support. So then Vs is called equivalent, strictly equivalent to V prime S prime if there is a symplectomorphism in the graded sense from between the cotangent bundles such that F star of S prime is equal to S, and it's called stably equivalent if they become equivalent after tensoring with these trivial solutions. If V times t with s plus some xi star yi. So here you have can have an infinite sum, but finitely many terms in each degree is equivalent to v prime cross t prime s prime maybe for some trivial solutions tt prime. So t is an affine space, and right. Okay, and theorem. So given x is 0, as above, there exists a BD variety we support x is 0, and it is unique up to stable equivalence. So this is our main result, and so the existence part is basically what Batarin and Wilkowicki described. So what you do is you first construct this underlying derived scheme, this part in negative degree, which is Tate resolution of the Jacobian ring. So it's a differential graded algebra concentrated in non-positive degree, whose cohomology is concentrated in degree 0, and it is equivalent to the Jacobian ring. And if you have this underlying scheme, you can reconstruct the variety by adding kind of dual variables. And then using the filtration I was describing, you can construct the solution of the master equation order by order. And at each step you have to solve some equation. So there is a priori an obstruction, but the obstruction vanishes because you have this vanishing of cohomology in negative degree. So this is the construction by Batarin-Wilkowicki. For the uniqueness, there are kind of two parts. One part was known in essentially Batarin-Wilkowicki, maybe a no title Boehm, which says that once you have this Tate resolution, this recursive construction is unique up to gauge equivalence, and this gauge equivalence is an equivalence in this sense. But then you have to show that it's independent of the Tate resolution, and there one has to work a little harder, because you know that any two Tate resolutions are related by quasi-isomorphism, and which is unique up to homotopy. But you need slightly more detailed result, namely that you can add some kind of trivial stuff to make them really isomorphic. Okay, so this is the existence. So instead of describing the details of that, I will speak for another 10 minutes or 15 minutes at most. I would like to describe some of the results of the cohomology. So we don't have much, but we can describe the cohomology in degree 0 and degree 1 in classical terms, and there is some kind of conjecture which I would like to state, an open problem if you like. So first of all, so we have a filtration, and so we have a spectral sequence to compute the cohomology. So this is about the BRST cohomology. So which is this sheaf O T star minus 1, the bracket with S. So the theorem that there exists, first part, there is a fourth quadrant spectral sequence degenerating at E2 such that, so let me write E2 PQ is, so you can really think of as some cohomology of so these are kind of coordinates, basis of your vector space, vector bundle, which you use to define V. But you can pass to the Jacobian ring with certain differential D1, which I will not describe. And these are in positive degree. This is for Q equal to 0. So there is a relatively explicit description of the complex. So D1 can be, if you know S, you can write it D1, but I will not write the detail. And Q is equal to 0 for Q different from 0. And okay, so this is the first statement. And the second statement is about convergence. So there is an edge homomorphism. Well, T star, I think I didn't introduce this notation. So this will be so is an isomorphism of Gradi's commutative algebras. Okay, so the algebra structure is relatively computable, but so the subtlety here is that this is there is no Lie structure here. So, of course, we know that the cohomology has a bracket, but the bracket is a little subtle because to construct this spectral sequence, you use the filtration, right? And this filtration is good for the product in the sense that if you take an element of filtration degree p, so in Fp, and one in Fq, you take the product, it will be in Fp plus Q. But for the bracket, it is less pleasant. Namely, if P and Q are large, then the bracket of an element of Fp and an element of Fq has large filtration degree, but it's not P plus Q. So this means that the bracket will behave badly in this spectral sequence. So to compute the bracket between two elements, you cannot just use the spectral sequence, you have to reconstruct the cocycles and compute the brackets in the original complex. So, but we can do this in very low degree. And so let me describe the cohomology in low degree, and there is a conjecture for higher degree that you can compute it in classical terms. So recall what is a Lie-Reinhardt algebra or algebroid. So Lie-Reinhardt algebra is a pair consisting of an algebra and a Lie algebra. So this is a commutative algebra. And this is a Lie algebra. And G acts on A by derivations, and G is an A module, and A is a G module, namely G acts on A by derivation, so there are compatibility conditions. So the standard example is a same axiom as A derivations of A. And right, so in our case, we'll take A to start with, we will take A to be function on X, and G equal L. L are this, so this is classical. We don't use S, we just use S0. So these are the vector fields such that psi of S0 is equal to 0. The algebra of symmetries. So then there is a notion of ideal of a Lie-Reinhardt algebra. Lie-Reinhardt ideal of AG is a pair I, H, where I is an ideal of A, H is a Lie ideal of G, and there are compatibilities. So the ideal should preserve the. I forgot. So I mean there are some natural conditions. These conditions ensure that if you take the quotients, you get again a Lie-Reinhardt algebra. And in our case, the ideal I will be the image of ds0, so the ideal generated by partial derivative. And L0 is, I will describe. So in our case, and L0 are kind of stupid symmetries. So if you take any function, there will be stupid vector fields which kill it, namely psi of S0 eta minus, so the span eta is 0 psi, where psi eta are vector fields. Okay, so this is a stupid way to construct symmetries. So now, and then we have the Jacobian ideal, L mod L0 is a Lie-Reinhardt algebra. And then to a Lie-Reinhardt algebra, there is also called the Ram complex, or Chevalier-Eilenberg complex. Is home. I think wedge GA or something. Always forget. With values in A, with some differential, and the differential is induced by the action of G and the bracket, some kind of natural lecture.
A linear form.
A linear, yes. G is an A module. And so, right, so now, so out of it you get a cohomology. Let's call it the Ram cohomology of the pair. And the theorem is that for P equals 0 and 1, that the cohomology of the BRST complex, call it BRST, is isomorphic HP the RAM of this Lie-Reinhardt algebra. Jacobian ring and quotient by the trivial symmetries. So for higher P, this is not known, and also there are competing definitions. So probably this complex is not good for, if G is not a projective module over A, one has to replace it by something better. But even if you replace it by something better, in degrees 0 and 1, it will be the same. So here it doesn't matter. So, but in general, one probably should use a better definition. But anyway, we cannot compute it for P equal to 2. But this does not give any information about the bracket. And so maybe I will write some. So the claim is that we can still describe the bracket, in this case. So the only bracket we can compute in this case, remember that the bracket has degree 1. So we have some map of this kind. And let me conclude by saying, giving a classical form in terms of the Lie-Reinhardt algebra of this bracket. Then I have some questions for you about this bracket. And then it will be over. Right, so remember that H0 was equal to the invariant. So you can also write L model 0 because L0 acts trivially on the Jacobian ring. So now what we are supposed to do is to send this to some element of B. Fg, the class of some element here, and Gfg will be a cocycle in Hom G, which is L model 0, Jacobian ring. So let me give this map. So let's so here we'll have some vector field tau, the class of a vector field tau. And let me explain how to construct this BFG applied to tau. So B of Fg. So how is the construction? So you start from tau. This is L by L0. So let's act on F with tau. So tau is the vector field. And I can add act with F. So let's take a class here, right? So here, this is a quotient, so you should take equivalence class. So, but let's choose a representative. So this representative is a function on here, but it's defined modulo partial derivative. But it is invariant, right? So this will be 0 in the Jacobian ring, but if you lift it, it will be something in the ideal, and the ideal is given by vector fields, right? So there will be a vector field which depends on tau and F acting on L0. Since it is invariant, it will be of this form. And now this B, of course, C will depend on choices. Now the claim is that F of G tau is F Xi tau F of G minus Xi tau G of F. Okay, so there's some formula like this that only uses a structure of Lie-Reinhardt algebra. So the questions for you is, first of all, is this kind of bracket generally defined for Lie-Reinhardt algebras in all degrees? Is there a formula for all degrees, or is it just in degree 0? And the other question, which is more embarrassing for me, is that I don't know any examples of BV varieties, or of functions S0, for which this bracket is non-zero. So both will be interesting. So if you can prove that the bracket is always 0, then this would show that the deformation theory of PV varieties is unobstructed. And but it would also be interesting to have an example where this is non-zero. But I don't know. Okay, so let me conclude with this.
I'm always supposed to ask naive questions. What are the beta eyes? I mean, intuitively speaking, in your spectral sequence, what are the beta eyes?
Right.
Can you?
Yeah. So they are. Right. So what is the construction? You start from. What you will have is something like this. So you will start from. You want to construct this variety T minus 1 of V. So V will be locally it will be some X times some affine space. So locally you will be able to construct it in this way. So some affine graded affine space, and and the functions on A will be some polynomial ring.
Yeah. My question was, what are the degrees and how many of them do you use?
So there will be finite remaining each degree. So the way you construct it is by taking the dual story. So if you so let me say so then the functions on the cotangent bundle will also have the dual variables bi. So maybe will be O x bi star. So this will be in positive degree, and the bi star will be in negative degree. So the bi star, you start by constructing the bi star because you first construct the Tate resolution. So the thing is that you will start with the Jacobian ring, which is O modulo dl0, and you will construct a Tate resolution. Namely, you will start by writing right. So what does it mean? So you will start with the Koszul complex. So the beginning of the Tate resolution will be of the following type. You start with OX, then you have CX, OH2 of CX, and so on. And so this is the Tate resolution. So of course you will start with this, but this might have cohomology in negative degree. So in the nice situations, a complete intersection, if the critical locus is a complete intersection, then this will be already the answer, and you will not need anything else. But if you have cohomology in negative degree, for instance, if S0 has symmetries, then you have something here. Then you will kill the symmetry. Suppose you have some vector fields, Xi1 up to Xk here, which are mapped to 0, so they are generators of the symmetries. Then you will start to construct new variables, add new variables beta 1 star, beta k star, whose differential is Xr. And then you go on. Possibly you have to add more and more, and so you get all these. And then you add the variables beta to be dual to those to get a symplectic manifold. And that's where the betas appear. And if you go to the spectral sequence, then you will forget about beta stars and remain with betas. So that's more or less the construction. So it is like in the case of Adef Popov, you had G, which were the symmetry. We had so these were the beta star. No, these were the betas and these were the beta stars. Or the other way around. Yeah, no, it's like this. start at the basis of G star.
I have a question. What I remember from the BD formalism is people have an action S0, they want an effective action S, and sometimes there is a, sometimes this was explained by Merkulov in terms of homotopy transfer theorem for Lie bialgebras. Why the kind of graph, I mean the Feynman graphs, they correspond to the graph that we have for this homotopy transfer. We have something like this here, I mean some kind of homotopy interpretation of the construction of the BD variety, or?
Can you repeat what would be a homotopy interpretation of it? So the Feynman graphs appear, I think, when you integrate over. So the Feynman graphs appear when you have the solution of the quantum equation.
Yes.
And then you want to integrate, right?
Yes.
And now you can integrate over part of the variables.
Yes.
And you get a function of the remaining variable, which is again a solution of the master equation. And the relation between the two can be expressed in terms of Feynman diagram.
Yes.
But here we don't integrate yet, so this would be the...
Okay, so this is my question. Any question? Thank you very much.